If you were to sit down with your smartphone or laptop and try to take it apart, would you be able to identify the makeup of these devices? Like, would you know the parts inside, or the main ingredients, if you will? Most of us have no idea how our computers or TVs function. It's a kind of technology we're obviously familiar with, but unsure how they work. And you could say much the same about semiconductors. They're the main ingredients in modern technology and are perhaps the most significant in the evolution of devices like TVs, radios, military systems, and more. To understand modern technology, though, is to understand the science of semiconductors. And in recent months, semiconductors have become the center of a heated geopolitical battle, one that revolves around the development of the most advanced forms of AI.
We'll be putting a tariff on of approximately 100% on chips and semiconductors. But if you're building in the United States of America, there's no charge, even though you're building and you're not producing yet in terms of... And we thought it was very important, obviously business-wise, but we thought even in terms of national security to have this large percentage of the chips, semiconductors, and other things that they make the most important product, and not a product that you can really copy.
As the pressure for AI continues to grow, so too does the pressure for advanced AI chips and the pressure for semiconductor production. It's the reason why the United States has focused much of its foreign policy on tech, using export control policies and trade deals to ensure they're staying ahead. For decades, semiconductors have been called the oil of the information age. But where oil is a natural resource extracted from the ground, semiconductors are the product of the human mind, and they're expensive. So how do semiconductors actually work? What does it take to produce them, and who's leading on those innovations? I'm Jennifer Strong, and I've been covering tech for more than 20 years. In this episode, we're going to explore how semiconductors came to be such a hot topic, and what that says about the future of AI. Welcome to The Next Innovation.
My name's Don Clark. I'm a longtime tech journalist, been following the sector for about 45 years. Currently, I write about semiconductors for the New York Times, but I was 23 years at the Wall Street Journal covering that sector. And in the 90s, semiconductors was a very mainstream topic. Everybody knew what the chip was in their PC and how fast it went and who supplied it. That kind of went away with the smartphone revolution. People didn't know that sort of thing. It was personal computers. Personal computers were as hot as AI is now. I mean, if you can imagine that. Everybody had to have a PC. This was when the internet was first coming on and even before the internet came on.
Millions of Americans own a personal computer. If you're one of them, you can now glimpse the future with nothing more than a modem, a phone line, and a few dollars a month.
Just what is this main artery of the information superhighway?
Well, it's become a place where people are publishing information. Right. So everybody can have their own homepage. Companies are there, the latest information. It's wild what's going on. You can send electronic mail to people. It is the big new thing.
If you think about the hype driving AI innovation now, it's not unlike what the world experienced in the mid-90s. The internet was really growing, giving life to an unknown digital universe full of opportunity. It was the Wild West. If you had a dream, chances were you could make it happen on the internet. Getting connected to the internet, though, meant having a personal computer, and that meant more production of PCs that companies like Microsoft and Apple were developing, which in turn meant more production of semiconductors. Computers started gaining momentum in the 1970s, as businesses and global corporations noted how they sped up production. But it was during the 90s that semiconductors got popular, like Don said. Everyone was curious to know how computers worked and if the chip operating their computer was the most advanced. But how exactly do they work?
Well, semiconductors are needed for some very basic functions in the world. If you want to add two numbers together, if you want to store a piece of information, if you want to amplify a signal, make it louder, basically you need electronic components to do that. And the story of semiconductors is about putting more and more of those tiny components, like transistors, into a smaller space on a piece of silicon about the size of your thumbnail. So Basically, they're in every product you can imagine, from your smartphone to your light switch to your, smart vacuum cleaner to your drone to your phone. Everything relies on semiconductors.
Think of semiconductors as the brains of modern electronics. They enable advances in medical devices, defense operations, transportation, quantum computing, and Wi Fi. The average smartphone today has far more computing power than the computers NASA used in the 60s. Much of this thanks to the development of semiconductors, which is what makes them so crucial for AI.
So basically, AI is driving incredible demand for semiconductors right now. So the industry, which had been expected to hit $1 trillion in revenue like in 2030, it's actually going to hit $1 trillion in revenue this year largely because of the AI boom. One of the things to keep in mind about the chip industry generally is that the price of chips can be very tempestuous. And so right now, the AI players and the people supplying memory chips, which are key for holding data in semiconductors, those companies can charge a lot of money for their products. So consequently, that's what's going up in the revenue number of the semiconductor industry, is largely the pricing has gone up really high because of the demand for AI.
Just like in computers, semiconductors are crucial for the speed, power, and energy needed for AI data processing and much more. They're what makes it possible for ChatGPT and Google Gemini to run smoothly on your smartphone. In other words, without semiconductors, AI advancements would not be possible. And in the current landscape of AI technology, the inherent race between the United States and China revolves around the production of chips.
NVIDIA, which designs the most advanced chips and the most widely used chips for AI, they have their chips made by TSMC in Taiwan. So TSMC is called Taiwan Semiconductor Manufacturing Company. That's a huge company that builds chips to order for hundreds of other companies, and it has the most advanced manufacturing processes in the world. And so now there's lots of talk about, China claims Taiwan as its own. So what would happen if, for example, China tried to invade Taiwan or blockade Taiwan or something of that nature? And semiconductors are now a strategic component. For example, the U.S. would be in a bad position if certain chips, say for our military weapons, we couldn't get them, and if they were in the control of another country. So just about all the major domains of the world are coming to that same conclusion that we're probably not going to replicate Taiwan and make all our chips ourselves, but it's really risky to have all your supply concentrated in one area that you don't, geographic area that you won't control.
Back in 2020, during the pandemic, global supply chains took a hit. It revealed vulnerabilities in the system and what happens when one country holds the biggest reserves of a resource. And it's part of why so many, including countries like China, grew concerned over Taiwan's dominance in the semiconductor market.
China has often been called the workshop to the world. They make all kinds of things for us, for the Western world. And semiconductors is a place where they've historically been behind, because semiconductor factories are not about lots of hand labor. They're about very, very complicated, expensive machines. You're taking a silicon wafer and you're doing incredible things to it, chemicals and all kinds of processes. And, it's a really high-tech process. And so they've been able to join that business, but they can't make the most advanced chips because basically, the West, that is to say America mainly, won't let them get the most advanced chip-making machines. So they've done a good job, up to a certain level of technology. So they can kind of make the sort of less complex chips that are used in cars and certain kinds of applications. But they're pretty much frozen out of the most advanced chips for artificial intelligence.
Like Don mentioned, TSMC's position in global semiconductor production means they're a geopolitical target for China, causing concern among businesses and politicians around the world, including the United States.
So consequently, during the Biden administration, there was a piece of legislation in the U.S. called the CHIPS Act, which put about $50 billion into making U.S. Facilities for semiconductors. And Europe has tried to do the same thing. So the governments over there collectively put money into attracting chip makers.
The United States semiconductor industry contributes to just over half the global market share, exporting about 70% of the global industry. And in 2023, just as companies like NVIDIA and the AI boom became household phenomena, the United States made over $200 billion in chip sales, which is why the U.S. and Europe are investing in their own facilities. Still, designing and building infrastructure made to produce high-tech devices is costly and laborious. For a major tech company like Intel, building a semiconductor plant, or chip fab as they're called, takes almost 5 years. It's a huge endeavor that requires upwards of 6,000 workers and about $10 billion.
So you take a piece of, first you have the fab, the factory that makes a chip. So that's a little, it's a little silicon square. And then that, that won't do anything for you. So you need to wrap it in a sort of a package with connectors so that you can plug it into a circuit board. And that circuit board itself is a component that will go inside your computer or your phone. And there'll be other components on there. There'll be memory chips, and there'll be storage, and there'll be communications, and all kinds of other components. So rare earths go into various components, including semiconductors themselves. If you want to step back, the machines that make semiconductors, have all kinds of components from around the world. The most important of those machines is a thing called a extreme ultraviolet lithography machine, and it comes from one company in the world, ASML in the Netherlands, and it in turn relies on a German company called Carl Zeiss to make these incredible mirrors. So each one of these machines, they have components from around the world, and that individual machine costs $200 million just for that one machine. This is the main reason China can't make the most advanced semiconductors, is because we won't let them have that one machine. And the reason they can't build it themselves is largely because of those mirrors coming from Germany. It's a pretty complicated picture.
In an effort to understand how the demand is shaping approach and innovation, I spoke to 3 leading entrepreneurs who are responsible for carrying out the designs, constructions, and quality control of chip fabs, like the architecture,
My name is Seamus Guyder. I'm an architect with RKT.
the resource distribution,
Okay, my name is Tony Woods. I'm the managing director of the Midland Group.
and the management software.
I'm Dan McAllister. I'm the co-founder and CEO of IDA Solutions.
These companies have worked with clients around the world to ensure that high-quality fabs are delivered at a timely and cost-effective rate. But how is designing and building a fab different from any other sensitive campus, like, say, a hospital or an airport?
I think you might be surprised. A lot of the principles are pretty similar, whether we're designing a housing scheme or a hospital campus or a semiconductor campus. Early stage design intent, be that a master plan, there's always constraints. In this particular industry, there tends to be more focus on security and speed of delivery, and also consistency in terms of a reliable design team, a reliable timeline, cost certainty. So a lot of the principles are there. There's always that initial sketch and that design thinking that goes into this. When we look at larger semiconductor campuses, there's efficiencies to be made, and that initial sketch can help with that efficiency. So by that I mean, if we take a sort of typical scheme where we're looking at, I don't know, say a 100-acre site. A 100-acre site, we might be producing 40,000 wafers per month. And to be able to design that site, to take the fabrication, but also the offices associated with that, the wastewater treatment, all of the ancillary uses is designing. So there's still a huge amount of focus at an early stage to make sure those adjacencies are correct, make sure we have the uses beside the alternative uses. And we really just want to make sure that we have a strong and robust master plan before we get into the next stage of design, which would be the more detailed stage of designing a facility.
As an architect, Seamus is responsible for working on different sections of the fab. On any given project, it may be to design an office or an interior element of the campus. But for bigger projects, like an entire campus, the process can be more involved. It starts with what's called a feasibility study, which, as the name suggests, determines if the design is practical.
So a feasibility study would be at the beginning of a project, and we do quite a lot of this work. And again, this would be for an existing client, and we look at a site. So the efficiencies that we found in co-locating or creating a campus of semiconductors tends to be sites in the region of 120 to 140 acres. So that would be about 50 to 70 hectares, and that would be producing 40,000 wafers per month. That breakdown, it would predominantly be single story. So working from the outside of that site in, we tend to use the landscape to create space for our storm water, which takes up quite a lot of the site, again depending on the location, car parking, infrastructure, roads. So all of the sort of backbone of how we get to the site and how we service the site is incredibly important. As we move into the site, the fabs themselves, a typical fab, we might see that being about 25,000 square meters, so about 250,000 square foot. But then ancillary to that, we'd have our central utility building, we'd have hazardous production facilities, admin, pro buildings, the wastewater treatment facilities that might be centralised. The offices are very important, so the front door to these buildings and where people can work, and they might be up to about 6,000 to 7,000 square meters per fab. So if we're thinking of a campus across 100 acres, that might be 10,000, 15,000 square meters of office space. So there's a huge amount of building that can happen within these campuses, but really breaking those down into manageable chunks. So the fab being 25,000 square meters and maybe having up to 6 within a campus setting. Within that 100 to 150 acre site, we feel is quite an efficient layout.
Part of building an efficient fab is also about ensuring that it's sustainable. Semiconductor fabs can be notoriously energy intensive, on occasion using up to 100 megawatt hours of power every day, or the equivalent of powering almost 16,000 homes. It's also the reason why there needs to be a reliable source of power. A cutoff at the source of energy could threaten a month's worth of chip production.
We can reduce our operational carbon by minimizing the redundant HVAC units, say. And really what we strive to do is to reduce the reliance on those HVAC units as much as possible. So we still need them if there's a peak in temperature. So it's about reducing our operational load on those buildings as much as possible. And there's lots of little ways to do that. So we work very closely with our sustainability team to look at smart solutions. So ongoing monitoring of it's easy to design a sustainable building. It's a little bit more challenging to monitor and make sure that building is working as it should be. So it's something that we take pride in, that we'd always go back and see how our buildings are performing, and make sure if they're not performing that we fix them. And it's very common in the building industry that buildings don't perform as they should. So I think that ongoing returning to your building and making sure you know how well it's doing and fixing it if it's not is important. But a lot of the key decisions at an early stage, even if you look at a campus, there's efficiencies not just in terms of cost but also in terms of energy use, to centralizing, be it wastewater management. There's also decisions that are made in terms of natural air intake, decreasing our reliance on air handling units. And there's also a much bigger discussion and need for our governments and our bigger stakeholders to ensure that land is zoned correctly so that these buildings can be built in the right locations.
But the importance of sustainability goes beyond the environmental perspective. Ensuring that fabs are efficient could lead to less labor, which in turn could lead to fewer injury risks. And with smart technology could also lead to a faster completion date. Midland Steel is a reinforcing steel supplier specializing in off-site rebar solutions. Rebars, or reinforcing bars, provide the pillar support for walls and a building's general structure. For a semiconductor fab, they're essential because they serve as the infrastructure's foundation.
What we do as a company in Midland Steel, I suppose, is that we have extensive experience in building concrete frames, and every fabricating unit that's built for the semiconductor facilities all over the globe all have concrete frames.
This is Tony Woods, Managing Director of Midland Group, the parent company of Midland Steel.
They have very heavy civils units in the bases of the semiconductor facilities to establish and take the load and weight of all the plant and machinery that goes into it later, and the mechanical and electrical side. And in order for the chips to come out at the other end of the factory, eventually when the facility's opened, there's a lot of wash, there's a lot of chemical that's used and stuff that has to be recycled. And there are some very heavy civil structures and tanks that they build in order to deliver their product at the end of the day. What we bring to that, I suppose, is a company that is experienced in concrete frames, but also knows rebar intensely.
He comes from a background of iron workers and steel fixers, and his mission at Midland Steel is to ensure the safety and wellness of its on-site workers.
In 2010, as a company, we were the first company in Europe to embrace the BIM process and 3D rebar detailing. What that was allowing us to do was allowing us to engage and collaborate with the design engineers by showing them in 3D dimensional viewing how we would actually fabricate the rebar and then deliver it in a unit that's pre-made in a factory rather than doing it on site. We further went on then as a company, invented a product called Faster Fix. And that Faster Fix process now is delivering the concrete schedules and the schedules for the opening of fabrication facilities, semiconductor facilities across the globe, 75% faster, but with 80% less labor on site. And what we were trying to do is address the problem that we have in two areas. Our first and core responsibility was that we wanted to improve health and safety on site. And we saw that with rebar, the amount of injuries in our construction industry, the most of those injuries occur from rebar fixing, placing, and iron workers. So it is a very tough job when you're out in the field and you're trying to place rebar loose. So we decided to do something different with that and bring it back into industry by taking it into an off-site environment and inventing a product called Faster Fix, which is all done in a factory to a quality process and then delivered on site ready for placement with 80% less labor, but it's 75% faster.
Tony works closely with general contractors at the construction stage and in post-construction reconvenes with the engineer and the cost consultant. Faster Fix ensures that everyone is on the same page in terms of planning, production, and sustainability.
At construction stage, when the general contractor is appointed, he then is included into the model, and there's full transparency between all of the surveying, the activities, the setting out. Everything can be coordinated through that 3D model principle. The surveying and placement of product on site and the setting out on site starts with the coordinates from the model. We fabricate the rebar within that model coordinate. So when he sets it out and we place it to the coordinates, every bar is millimeter perfect. That whole 3D environment is fully collaborative. Everybody can see what's happening. There is a full traceable process from the point of view of production, then right through to delivery. And we have a color-coded model that on a snapshot on your phone, you can see exactly what level of productivity we're making and where we are in the building's progress. You can also monitor and budget all of the activities on site, and you can monitor that against your schedule of when your milestones are to be met.
Much of what Faster Fix does is provide a communal working tool for the many moving parts during construction. Like Tony mentioned, it creates visibility and cooperation. And for complex semiconductor fabs, these kinds of tools are essential for identifying tiny mistakes that could be expensive and cause delays. Dan McAllister does something similar for quality control. He's the co-founder and CEO of IDA Solutions.
Our software does document control, it does the quality side of things, and it does progress tracking. And to just to try and coin the phrase, and now to how does IDA exactly help out in quality on a project? Because we're software. What it does is it picks up a check sheet, the correct check sheet that a client would want. So we're adhering to their standards, and that when they're doing a walk down, for instance, of a certain thing called like pipework or installation of a piece of equipment, the correct check sheet appears with a load of logic in it. And that's what IDA does. And then if you've got 1,000 check sheets to do and you've done 900, that's your progress. You're 90% there. What we do is we take the client requirements, and they might have their own specifications, and we digitize those forms. And those forms basically are what the users would have to answer. They'd have to make notes on. They'd have to log defects throughout the projects, and they do that in IDA. So instead, we've eradicated permit books. So permit books, would be these big books with the carbon paper in behind them. You'd be filling in permits left, right, and centre. An engineer would on behalf of the team that are going to go down site. So they got to go through the permitting workflows. We digitize that.
Both Midland Steel and IDA Solutions are conscious of how challenging big fab constructions can be. The countless moving parts, the many employees on site, the mountain of paperwork, things can get out of hand and lost in the process. But their products enable agency for the workers. They allow the engineers, supervisors, document controllers, and others to be mindful about every step of the project.
So the difference between semiconductors seems to be getting bigger in the footprint of the actual building. They seem to be trying new things. Everything on a semiconductor, for me, in my experience, seems to be getting bigger and bigger. You need more and more people on the project. You got off-site manufacturing as well. You're involving them, but they're just massive projects. You got to build them. There's multiple trades. In some cases, there could be more than one general contractor as well, which we've experienced. So that's a challenge itself because they got their own processes, but there's multiple contractors, trade contractors on the project, and they're large projects. It takes them at least 3 years to really get anywhere on these projects, and then you got to commission them as well, which is an extra 2 years.
The policies set forth by the United States and Europe, like the U.S. CHIPS Act, implies that investing in semiconductors is no longer about investing in the market of smart technologies, nor is it about supporting the production and distribution of computers, smartphones, TVs, you name it. It's about investing in the future and about protecting the future. The theory is, if Western countries reduce their dependency on Chinese or Taiwanese resources, they'll become more technologically independent. And ensuring that countries can develop certain parts of essential technology is also a matter of national security. Thanks for listening to The Next Innovation. This series was produced by Situation Room Studios and powered by Enterprise Ireland, investing in the next wave of innovation. Our executive producer is Christine Barada, and our senior producer is Sharon Barrero. Lisa Pena and Leila Sharawi are the associate producers. Additional production assistance by Global Situation Room. And a special thanks to Don Clark. I'm your host, Jennifer Strong. Until next time.